Okay, here we go with 6.3, similar polygons. Similar polygons they're similar, polygons are similar if we have corresponding angles between the two polygons that are congruent. So angles will be congruent, and then corresponding sides are going to be in the same proportion. Sides will be proportional, so they will reduce to the same ratio. They're going to be in the same proportion. Angles are congruent. Our similarity symbol is a little squiggle. I don't always make a very good one, but it's a little squiggle. That's your similarity symbol. So in the following diagram, we have a similarity statement. This is a similarity statement right here. It tells me that triangle RST is similar to triangle XYZ. So that means that the angles are the same measure. Angles are the same. And the sides will be in proportion to each other. So we're going to list the pairs of congruent angles. So my pairs of congruent angles. Now, a similarity statement works exactly like a congruency statement does. It tells me what pieces are corresponding. And so if I want the angle that corresponds to R, I have to look up here at the similarity statement and say, okay, R is in the first position, and so in the corresponding triangle, X is in the first position. So the congruent angles would be R and X, and then in the second position we have angle S. It will be congruent to, in the second triangle, it's going to be congruent to angle Y, and then angle T is going to be congruent to angle Z. And so my angles are congruent. So remember, angles are congruent. Now we need to check in B here that the ratios of the corresponding side lengths are equal. We want the ratios to be equal. So let's look at the corresponding sides. If you look at the first two letters, let me use a different color here, R and S are the first two letters in the first triangle. So RS, and that would be corresponding to, in the second triangle, XY, number 1 and number 2, XY. So let's look at the ratio of RS over XY. And that ratio is 20. RS is 20. XY is 12. And then let's simplify that ratio. That ratio is going to simplify to 5 over 3. And so that means that the other ratios of the other pairs of corresponding sides must simplify to this same ratio for them to be in proportion, in the same proportion. So let's check the other ones. We've got ST, let's check ST over YZ. Okay, ST is 30. We have YZ, which is 18. And let's simplify 30 over 18, and that also simplifies to 5 over 3. So the last one we have then is TR, and that's going to correspond to, and if you look at the triangle similarity statement, T is the last one, R is the first one, so third and then first. Z is the third, then X is the first, so this would be ZX. So again, order of letters is very important here on similarity also. TR is 25, ZX is 15, and that's going to also reduce to 5 over 3. And so since they all reduce to the same, then they are in the same proportion. So on C, it says to write the ratios of the corresponding side lengths in a statement of proportionality. Well, my statement of proportionality is just going to say that the ratio of RS to corresponding side XY is equal to the ratio of ST over YZ, which is equal to the ratio of TR over ZX. So that would be the statement of proportionality, that all of these ratios of corresponding sides are in the same proportion. Okay, let's look at scale factor here. Now, scale factor, again, you can read about scale factor on page 373. The scale factor is the ratio of corresponding sides in similar polygons. So my scale factor will end up being a ratio, and it will be of corresponding sides in similar polygons. So when we know they're similar, or we may have to prove they're similar first and then come up with the scale factor, which is what we're going to have to do in this example. This means that the ratio of the ratio needs to be, though, one side from each figure. And sometimes when we start looking at triangles, people want to put together a ratio of two sides in one triangle equaling two sides of another triangle. It's fine for solving, but when we talk about the scale factor, you need to have one side from each figure. That way we're comparing the two figures to each other. So one side from each figure. In this example, we're going to determine whether these polygons are similar, and if so, we're going to write a similarity statement, and we'll find the scale factor. So the first thing we have to do is look at, first part here, is let's talk about angles. What do we know about the angles for similar polygons? We know that the angles all have to be the same measure, and that's corresponding angles. And if you look at, they tell me what letters to use here. Z, Y, X, W, and F, G, H, J. So in that order. So we've got angle, let's just take them in order. Angle Z. Is angle Z congruent to angle F? And yes, angle Z is congruent to angle F. Look at the next one. Angle Y. Is angle Y congruent to the second letter, angle G? And they are. They have two tick marks, so it is congruent to angle G. Angle X is congruent to third letter, so third letter of the second one would be angle H. And is X, yes, congruent to H? Three tick marks, so it is congruent. And then the last one we have, angle W, is congruent to angle J. And those are both 90 degrees. W is 90, J is 90. So those are congruent. Okay, let's do a next part here to check whether or not they are similar. We're going to check their ratio of their sides. So remember corresponding sides. And we can do it by the letters as they're written. ZY should be in the same ratio to FG, ZY to FG, those two corresponding pieces, should be in the same ratio as all the other corresponding sides. So let's check those. We've got ZY corresponds to FG, and that ratio ZY is 25, and FG is 20, and that's going to reduce to 5 to 4, 5 over 4. Okay, let's look at the next one. Let's do YX. YX, second and third letters, to GH. So YX is 30, and GH is 24. And let's reduce, there we go. Sorry if you can't read my handwriting. 30, tell you what, I'm going to go back a little bit because that does look pretty bad. 24. So 30 over 24 also reduces to 5 over 4. So we just got to make sure that all of these reduce to the same thing. Let's do XW over, that's the third and fourth, so HJ. So XW 15, HJ 12, and that's going to reduce to, divide both by 3, and that's going to reduce to 5 over 4. And then our very last one would be the fourth and then the first letter, WZ, and fourth JF. WZ is 20. JF is 16. So you see, if you have to prove similarity, you have to show that all sides are going to reduce to the same number, 5 over 4 here. In this case, these polygons all reduce to 5 over 4. And since they all reduce to 5 over 4, here's my similarity statement. So this would be the last part of the problem. The similarity statement would say, okay, z, y, x, w is similar to, so there's your squiggle line, f, g, h, j, and the scale factor now, this is one place we need to talk about the scale factor. The tax way and the way that the book tell you are different. The way that the book tell you to write the scale factor is that if I compared the sides from the first one to the sides of the second figure, I get 5 over 4. And so the book way is going to say that the scale factor is 5 over 4. I'm going to put this in parentheses. This is the book way. The book way says that the scale factor is going to be 5 over 4. But here's what we need to look at. Between these two figures, if I'm starting with z, y, x, w and going to that direction, I start with, in the way, the order that they give me in the problem is z, y, x, w first, going down to f, g, h, j. So if you look at it from this first figure to the second figure, I'm getting smaller. My figure is getting smaller. And so if I want to get smaller, I'm going to need to multiply by a smaller number. I'm going to need to multiply by something smaller than 1. I need to go the other direction, 4 over 5. Now this is the tax way. And we've always seen before that the tax way is the way we had to learn it. If I'm going smaller, I need to multiply by the number smaller than 1. So I need the fraction to be 4 over 5 if I'm getting smaller. If the letters were reversed, the way we're referring to the figures here, if it was reversed and I was getting bigger, then I would have to multiply by a number greater than 1. And so I would be using that one if I was getting bigger. So honestly, that's the tax way, and we've always done tax. We're still not sure at this point how we're going to see this ratio come out with the EOC testing. So we're going to look at it the tax way, the way we've always seen testing done, is that if your figure is getting smaller, so I'm going from 1 to 2, if I'm getting smaller, I need to be multiplying by my scale factor has to be smaller than 1, which would be this one. If I was getting bigger, if this was my first figure and this was my second figure, if I was getting bigger, then I would be multiplying by a number greater than 1 to get bigger. And so I would be using the book's way, or the 5 over 4 one. Okay, we'll talk about that one some more in class. All right, let's look at this example. In the diagram, these two triangles, triangle DEF and triangle MNP, are similar. So DEF is similar to MNP. And so I want to use the scale factor to find the value of x. So we're going to use the scale factor here. Okay, so let's look at from DEF, that's number 1. That's the one that's listed first. So I'm going from smaller to larger. And remember, we don't want to always go by what the pictures look like. Okay, to do them backwards. Don't go by what the pictures look like. Let's go by what we know. We know that these side measures, 12 has to be, it corresponds to 16, so 12 is the smaller number here. So the figures are actually a little bit backwards. Go by what you know. This side 9 corresponds to MN, and it's smaller. DE is smaller than MN. So I'm actually, when I go from DEF to MNP, I am getting larger. So the scale factor that I want, to set up a scale factor, I already know they're similar. I don't have to prove it. Setting up a scale factor then means if I'm getting larger, I want the larger number on the top, because I would be multiplying by, or sides, by a fraction bigger than 1 in order to get bigger. Some number bigger than 1 will enlarge my figure. So we're going to use the 16 on the top over 12 on the bottom. So this is going to be my scale factor. Let's reduce that. So my scale factor is 4/3. That is the scale factor. SF for short, scale factor. So now let's solve for x. We've got my scale factor of 4/3, and I used those two because they're the, I could have used the 9 and the 12. Let me show you that. I could have used 12 over 9. You need two corresponding sides that have numbers for them so that you can set up your scale factor. All right, so now that I have that set up, x is what I want to solve for right here. Remember that we used the larger number on the top, and so of the corresponding ratio over here, I've got to use the larger number. So x corresponds to 20. That means that 20 needs to go on the top, and x needs to go on the bottom. And then you'll remember from our last section, to solve this, we cross multiply. So 4x equals 20 times 3, which is 60. And so my x is going to equal 15. And there's your answer. Okay, the last thing we need to talk about in this section then is the perimeter of similar figures. We want to look at the fact that the ratio of the perimeter of similar figures is equal to the ratio of corresponding side lengths. Perimeter is a single unit. Remember how we just add up all the sides to get the perimeter. And so if I'm in feet and I add up the sides, they're all in feet. So when I add them up, I'm just going to be in feet. I don't change. It's not like area where I square something. I'm in singular units with ratio or with perimeter. And so what we can use is the scale factor. And the scale factor is the ratio of the corresponding side lengths. Isn't that my scale factor? Right? So we can use scale factor here too, which is just the ratio of corresponding side lengths. Let's look at the example. An Olympic pool is rectangular with a length of 50 meters. That's supposed to be an L. And a width of 25. A town is building a new pool that is similar in shape but only 40 meters long. So its length is 40 meters. So the first thing we want to do is find the scale factor of the new pool to the Olympic pool. New to Olympic. So if I want to go from new to Olympic, I'm getting bigger, right? And so if I want to get bigger, I've got to multiply by something larger than 1. If I'm getting bigger, the bigger number is going to be on top. And so I want the 50 over the 40. Scale factor is 50 over 40. Now let's reduce that to 5 over 4. So there is my scale factor. Now I used those sides because I had lengths for both of these. I didn't have width for both. So what I need to do now is, this is the scale factor between the two. I used the measures where I do have a measure for each of those lengths. That's how you set up your scale factor. Now we're going to find the perimeter. So the first thing I want to do is figure out, well, what would be the perimeter of the Olympic pool? I can figure that one out, right? Because I've got 50 for the length and 25 here for the width. So I've got two 25s plus two 50s. And so that's going to give me the perimeter of the Olympic pool. So let's find the perimeter, and I'll put just an O down here at the bottom. We're going to find perimeter of the Olympic pool. And the perimeter of the Olympic pool is going to be 50 plus 50. We'll just add them all up. 50 plus 50 plus 25 plus 25. Add up all your sides. And we're going to get 150 meters. So that's the perimeter of the Olympic pool. Now, to find the perimeter of the new pool, we have to use the scale factor. Since we're in single units here, we're just talking feet, and perimeter is still in feet, or meters, I'm sorry, meters. We're in meters. The perimeter is in meters, and my ratio of sides is in meters. My side lengths are in meters, so we just use the scale factor. We have, let's look at it this way. Perimeter of the Olympic pool over the perimeter of the new pool. We'll do P of O, perimeter of Olympic, over P of N. And this is, we're going to use the scale factor, 5 over 4, and that's going to equal the perimeter of the Olympic pool, which we do know, over the perimeter of the new pool. We don't know that one. So we'll use P, and we'll give it a sub in there so we know we're talking about the new pool. We're going to cross multiply. 5 times that P, this gives me 5 times P, and that equals 4 times 150, which is 600. And so when I divide both sides by 5, the perimeter of the new pool, I guess I should have put an in right there, the perimeter of the new pool is 120 meters. So perimeter, you use the scale factor just like you would with sides if you're solving for a side. To find the perimeter, you've got to find the perimeter of one of the figures that you can, and then set up your ratio using your scale factor, and this is your scale factor right here, 5 over 4. And you will use scale factor to solve for the missing measure. All right, see you on the next video, or well, I'll talk to you on the next video.